Hello everybody, thank you for listening to my speech. My topic is preliminary exploration of physically interpretable CNs for SAR image understanding. My topic will divide from four parts. The first is background, the second and third are physical scattering signatures extraction from polarization and wideband perspectives respectively. And finally, I'll give you conclusions and the future work. First, the background. We know polarization modes and microwave bands play vital roles in SAR pulsar systems, and the physical scattering mechanisms usually refers to surface scattering, volume scattering, multiple scattering. These are the most commonly investigated ones. And first I will give you physical signatures extraction from polarization perspectives. We know for a fully parametric SAR images, we can get the physical analysis and do some geometric analysis to get the physical information and the geometric information, and finally to serve for the pulsar applications such as classification and detection and so on. But for single and dual parametric SAR images, it's usually hard to do this. So we consider a physically interpretable deep model. This model considers four factors. They are complex data form, learning capabilities, robustness of the model, and the model should be an end-to-end system. So for the method, first we do data preparations as the workflow shows us, and the basic the experiments are verified with DRS L-band SAR data. And the methodology is actually a contrastive regulated CN in a complex domain. And this method, the network, should be the input data, the output data, and the parameters in this framework are complex values. The operations inside the network are carried out in the complex domain. And this model can directly learn physical scattering types from Sinclair matrices with different polarizations. And with this model, we could explore the physically interpretable capability from the perspective of image polarizations. And in this method, we consider some natural characteristics in SAR. It's really unintuitiveness for SAR images, and it's difficult to distinguish, for instances located in boundary areas in the cloud's H-alpha division plan. So we propose a regularization term, which is actually a contrastive embedding to add to the basic laws, and they combined to minimize and to optimize the loss function to supervise the whole process. The basic loss is defined and selected from the complex valued mean squared error, mean absolute error, and the cross entropy. And the results we get from the L-band SAR data is this is from the single parametric data and the results, and also the dual parametric SAR images and the results. And also we demonstrate the generality of this method from another L-band SAR data. And this is the basic information of the data, and also the single parametric data, the extraction results, and also the dual parametric results. So the second part is from the wideband perspective. We consider the polarization, single pole and dual parametric SAR images are very limited to derive physical read signatures, while quad pole is capable for this, and the frequencies are usually different. So the challenges are less in two points. The first is the translation of physical radar signature is actually a nonlinear functional mapping, which requires a critically accurate mapping strategy, and this data misalignments and distortions are really severe between different SAR sensors. And the methodology is can be divided for composed with two parts. The first is stage 1 is data processing and data preparation and pre-processing, and then stage 2 we train a GPR model and predict polarization parameters and extraction of physical scattering signatures. This is experimental results is from SAR data and TerraX data. This is the TerraX image. It's HH polarization, and the prediction results of parametric entropy and parametric alpha angle, and we predict the physical scattering signature types. And the second is C-band Sentinel-1 image and SAR. This is the real Sentinel-1 image, and the predicted parametric entropy and predicted parametric alpha angle. Finally, we got the physical scattering signature types. And to verify the generality of this model, we used another Sentinel-1 data. It's the original data and the prediction results. And finally, we conclude from the 3 points, and in the future we could extend a generalized pulsar decomposition method and considers this issue from time frequency analysis and bi-coordinate representation. Yes, that's all. Thank you for listening.